Alright, so I'm making this video today to ask a question about minus signs and gravitationally stored potential energy. So this goes back to these slides in my gravitation lecture that involved this picture here where we're zoomed into the Earth and zoomed out. Okay? Now, what's always true is that when you're far away from the Earth and you're close to the Earth, we're always talking about more and less gravitationally stored potential energy. So in my slides, I made a point to say that there was more and less rather than an exact amount, because what we're really concerned with was a change in gravitationally stored potential energy. All right, so back to this slide here. This was the next one in that lecture. Now, what was happening here is this is always true. This potential energy curve is always true. And while I'm not talking about the linear part of this, we're not really concerned about that. If you want to learn about this, take electrostatics. But we're really concerned about this part here and how it's negative. Now, the math is for this expression came from calculus, from the Newton's law of gravity equation. So I talk about that during the presentation before, where we have the force of gravity is equal to big G, one mass, another mass, over their separation squared. Okay, so if you want to see how I got that again, take a look at that lecture. Okay? Alright, so some new sketches today. The minus sign was always there, actually. It just didn't matter before. So consider this. Every time you do an energy conservation problem, let's say, in this case, ball rolling down an incline, okay? We've always had an initial energy and a final, right? And we're talking about the total energy, and specifically, we're talking about how the EG changes, right? Now, if you ever wondered, like, why did it, for some problems like this, why did it never really matter if the ramp and the ball were actually on a table in a lab, right? And moreover, why didn't it even not matter where the lab was, right? So who was to say that this lab was not 50 stories up on a building where the height was now street level? Or what if it was below the ground, 50 floors below the ground? That never would have really mattered either. Okay, so the key phrase here is that we were very close to the Earth. Okay, and what we're really talking about is how it only changed from the beginning of the problem to the end of the problem. That's why we didn't care if it took place on a table or in a lab on the 50th story floor. It didn't matter because we're only concerned with the initial and final states of the system. All right, so when we're thinking about our regular, or let's just call our EG equation near the surface of the Earth, yeah, this was true, but it was really more correct to say that we're always talking about changes rather than exact values of potential energy. Okay, so it's really more true to say any change in height gave us a change in potential energy. So to reconcile the minus sign in the old equation, really, then again, you have to forgive me, these are informal derivations here, but here is our old FG equation, right, near the surface of the Earth, and if we say that it's at the surface of the Earth by using the equation for gravitational field strength, then we have this expression that we've been talking about for the last few days. Okay, calculus can get us here. And if we kind of do this is the informal, sketchy part. But if we think about, like, the location, we can resubstitute this back in. Okay, because G hit by an R is really just something like this. Okay, so our R was really that height that we were talking about. And we really were talking about negative values here. We just didn't talk about it, or it wasn't really important then. So here I'll give you an example. Okay, so in this problem that I introduced, like at the slideshow here, we could have started by saying that, okay, let's just say that there's 20 joules of energy stored gravitationally here. And we end up with 0 because it was at a height of 0, right? Just your regular problem. And let's just say we wanted to find the velocity, which is inside of this EK. Now, the thing is that the change in EG is always final minus initial. Okay, so we were able to tell, all right, well, between the initial and final states of the system, there was a change in EG of negative 20. So where'd that go? Well, it was stored kinetically, right? Okay, so that's like an old problem. Now, one way to think about this is that universally, what really happened was that we went from a state of more EG to less EG. So what does it matter if we made everything negative, right? So here we're still going from more EG to less EG. And notice that in these numbers that I made up, more negative 20 is for sure more than negative 40, right? This is just more than negative 40. Okay, so if we apply our change in EG equation, we'll still do the difference of final minus initial. So negative 40 minus negative 20 is equal to negative 20 joules, right? So these are in agreement with each other, and that's what's important, okay? Now, true, our LOL diagrams look very weird and different. So here, we still start with negative 20. We will end with negative 40, but we don't really care about we didn't really care about the minus sign. What mattered was that we got 20 joules for EK. Okay, so that's why both of these things will produce the same velocity if we get to that part. It was never really about exact values of EG. It was more about changes in EG. Okay, and this is actually a topic that you'll see discussed in higher levels of physics. I'm talking about like junior, senior year grad school level physics, and this is called gauge invariance. Okay, so I hope that answered the question about negative signs and the EG before versus the EG now. And before, I mean December rather than initial. Okay, so I'll see you later. Hopefully this helped.